Let's do another example. So in this example, I have a link and there is a slot cut inside this link. Okay, and I have a disk, should be a circular one, which is actually allowed to roll because there is a pin on this disk. So this pin that you see P is actually rigidly attached to the disk, and the slot is constrained in a way so that this pin P is going to slide inside the slot of this link over here. Okay, so just to show this to you in a better way, let me erase these lines so that you can see that the disk is kind of behind. All right, so that's what it looks like. So this is supposed to be a circular disk, pardon my drawing over here. Let's say that's the center. All right, now the question is that if, let's say, this rotates at a certain angular velocity, let's call it, I don't know what we'll call it, let's say omega 0. Okay, then what is the velocity of the disk? So we're looking for the linear velocity of this. At the same time, we are also looking for the sliding velocity of the pin P in the slot, right? So even though the pin P is rigidly attached to the disk, with respect to this link which has a slot cut into it, the motion of the pin P is actually of a sliding one, right? So if you as an observer stood at this link and you looked at this pin while this whole system was moving, you would see this pin P coming towards you or going away from you. Okay, so in this particular case, if omega is shown as clockwise, for a while you will see the pin P actually going away from you, right? Because the path of this pin P on the disk is this, right? So it is going away from you if you stood at the same place, and then after a while it will come closer to you, right? So the direction of the relative velocity is going to change as the wheel rolls or the disk rolls towards the right hand side. Let's assume that the disk is rolling without sliding, which means that there is a definite relationship between the linear velocity of the center of the disk and the angular velocity. Okay, so we're given omega, let's write that, we're given omega 0 of the length, which is clockwise direction, and we have to find the relative velocity of the pin P in the slot as well as the linear velocity of the wheel or the disk. Okay, so two unknowns. If we can generate one vector equation, then we can solve for the two unknowns. Okay, all right, so first of all, let's apply the test. What kind of reference frame we should use here? We will use the rotating reference frame because we can clearly see that there is a pin P which is sliding on a rotating rigid body, which is this slotted link. All right, so let's label some of the points. This is point O, that's point P. So let's write velocity of P. We need to show our reference frame, and again I'm going to show my reference frame in this way. I will attach it to my slotted link. So Vp equal to velocity of O, which is 0, plus omega 0 k hat, that's negative, cross r of P, which is to O. Let's say this distance is given to you as L at this instant, so that's Li hat, plus V relative, and we don't know the direction, so we'll assume it to be positive I hat. So that is minus omega 0 times L j hat plus V relative I hat, and that is the velocity of pin P. Okay, so that's one equation. So you can see it has two components, one along x direction, right? One along x direction, which is this V relative I hat, and the other one is minus omega 0 L j hat, which is in the downward direction. So the pin P has these two components because the link is rotating at the same time pin P is sliding out, right? Okay, so that's one perspective. Now let's look at the velocity of the point P from the perspective of the wheel or the disk. So we can relate it with the velocity of O. We can do that, right? We know its direction at least. So velocity P can be written as velocity of O, which is not 0 by the way, plus whatever this angular velocity is, right? Omega, let's call it omega 1. Okay, so omega 1 k hat, and that's going to be, kind of clearly that negative k hat, so negative k1, negative omega 1 k hat cross r of P, which is O. So for simplicity, let's assume that this point P is really directly above O, okay? I mean, we could be given x and y coordinate, but it doesn't matter. Let's say this is at a distance r above, okay? So how would we write R of P with respect to O, right? Which is what we want to write, R of P with respect to O. Actually, there's slight abuse of notation here. This is already O, so let me call this, what are we going to call it? We'll call it Q. Okay, so this is Q actually. So the center of the wheel is actually Q. So what is R of P is Q? Now we have to write this vector. Don't make the mistake of writing this as Rj hat, right? That will be wrong. Why? Because we have already chosen our coordinate system oriented this way. And that reference frame, and I can draw this again separately. So this is O, this is X, this is Y. Let's say this angle is theta. Then R of P, which is Q, is this vector. R of P is this vector. So what is that vector? This is theta, right? So R of P is Q is actually this quantity over here. Let me write this expression again. Is this minus omega 1 k hat cross that distance is R, so cosine theta along j hat plus R sine theta I hat. Okay, so let's call this equation 2, right? So we have expressions for velocity of the point P from two different perspectives. Those two perspectives are reflected in equation 1 and equation 2. Let's look at our unknowns. So omega 0 is known, right? Velocity of relative velocity is not known to us. And we also don't know what omega 1 is. We also don't know V0 is. So it looks like there are too many unknowns. But we know that if we enforce the no-slip condition on this wheel, then the velocity of the contact point is actually 0, right? And that means that the V0, we've seen this before, V0 is equal to the radius of the disk times omega 1, right? So we know that. So since we're looking for V0, we can write omega 1 in terms of V0. So this is V0 I hat. We know that velocity of the center of this wheel should be towards the right, minus omega 1 is V0 over R, and this is K cross R cosine theta j hat plus sine theta I hat. Let's simplify this. Cosine theta k cross j is minus I hat plus sine theta k cross I is j hat. So, one thing you would probably notice is that we're taking a lot of cross products. So your ability to do these cross products quickly can make a difference in the exam situations. Okay, so we got the velocity P, that's expression number 2, right? And now we can equate 1 and 2. So equate 1 and 2, what do we get? 1 is minus omega 0 L j hat plus V relative I hat equal to V0 I hat minus, this becomes plus V0 R over R cosine theta minus V0 R over R sine theta j hat. Okay, so on the left hand side, I had coefficient equal to the I had coefficient on the right hand side. I forgot to write I hat over here, so that's plus V0 times R over R cosine theta. Okay, and then we have minus omega 0 L equal to minus V0 R over R sine theta, right? So minus minus cancels. We get V0 equal to omega 0 times L times R over R divided by sine theta. So that gives you the velocity of the center of the wheel or the disk. Now we can substitute that in here, and that will give us the relative velocity, right? So we have two equations, we have only two unknowns, and we can solve for both of them. Okay, so in reality, this problem isn't any different from the previous example that we did. Okay, it's just that we replaced the crank, which we had in the previous example, to a wheel in this case. Now, how would you do the acceleration analysis? The acceleration analysis would proceed along similar lines. What you would do is you would write the acceleration of the pin P from the perspective of the disk, and then you would write the acceleration of P from the perspective of the slotted link, and then you would equate them. Okay. One thing I want to remind you is that you cannot use instantaneous center of zero velocity method whenever you're using a rotating frame. Okay, that is not something you will be able to use. So that method really applies only when you have a translating frame. Okay, now let's see how we will do acceleration analysis for this problem. Okay, acceleration analysis. So let's look at it from the disk perspective. So we want to write acceleration of point P with respect to point Q, which is the center of the wheel. So acceleration of P equal to acceleration of Q. We have minus omega. We are calling this to be omega 1. The angular velocity of the disk is 1. Okay, so minus omega 1 squared r of P with respect to Q plus alpha 1 k hat cross r of P with respect to Q. Now alpha 1 is the angular acceleration of the disk, which we don't know. Maybe that's one of the unknowns. And then that's it, right? So between these 2 points, P and Q, there is no relative velocity, there is no relative acceleration, because those 2 points are the same rigid body and distance between them is not changing. Okay, so let's simplify this. Acceleration of Q is the acceleration of the center of mass of the disk, and that will be along I hat direction, minus omega 1 square. R of P with respect to Q is this vector, which we have already written before, and that is this right here. So let's write that. So R cosine theta, that's j hat, I guess. Yeah, j hat plus sine theta I hat plus alpha 1 k cross, again the same vector. So this is a0 I hat minus omega 1 square r, and let me write I hat first and j hat next, plus alpha 1 r cosine theta k cross j is negative I hat plus sine theta k cross I is j hat. Okay, so let's collect all the I hat terms. We have a0 minus omega 1 square r sine theta minus alpha 1 r cosine theta plus we have minus omega 1 square r cosine theta plus alpha 1 r sine theta j hat. And that's the acceleration of P. Let's call it equation number 3 from the perspective of the disk. Okay, so what are the things that we know here? We don't know what A0 is. Okay, we do know what omega 1 is, but we don't know what alpha 1 is. So A0 is an unknown and alpha 1 is an unknown. Omega 1 is known, right? So you can clearly see that even if the question asks you to do acceleration analysis, you always have to do velocity analysis first. Because if you don't do the velocity analysis, you wouldn't get angular velocities. And then if you just jump to the acceleration analysis, you will see, hey, you have too many unknowns to solve for. Okay. Now, are A0 and alpha 1 independent of each other? No, they are not. Just as we know that the velocity of center of mass of the disk under no slip condition is its radius times omega 0, and we are using omega 1 here. So this is actually omega 1. This is r times omega 1. Similarly, acceleration by differentiation would be r times alpha 1, right? So actually alpha 1 is known in terms of A0. So if the question could ask for acceleration of the center of mass or it could ask for angular acceleration, it doesn't matter. If it asks for A0, we can write alpha 1 to be A0 over r. So in a sense, we only have one unknown in equation number 3, right? Either alpha 1 or A0, but not both of them. Okay, now we will also write the acceleration of point P from the perspective of the slotted link, right? And that will be a long expression because in the rotating reference frame, we have additional terms which take care of the relative motion between the point P and the point O. So let's do that. So acceleration of P choosing O as a reference point, which by the way is a fixed point, right? This point O over here is a fixed point, right? It doesn't move. Minus omega 0 square r of P with respect to O plus alpha 0 k hat cross r of P with O. What is this alpha 0? Alpha 0 over here is the angular acceleration. So this is omega 0, and then we also have alpha 0, the angular acceleration. And this angular acceleration could be clockwise, could be counterclockwise. Now, you know that the angular velocity could be pointing in the clockwise direction, but the angular acceleration may be counterclockwise, right? What would that mean? That means essentially that your angular velocity is going to be decreasing because angular acceleration is pointing in the opposite direction. If both of them are pointing in the same direction, that means the angular velocity is actually going to increase in that direction. Okay, so both of them could have different direction. Okay, so we will assume that in this case alpha 0 is also negative, so this would be actually minus alpha 0, all right? Plus 2, we have omega cross v related term, so we have 2 omega 0 k hat, and that's minus cross v relative, So V relative I hat, that's the correlates acceleration term, plus A relative, which we don't know, I hat, right? Okay, so let's simplify this. So R of P, oh, what is that position vector? That position vector is this vector from here to here, right? That's this. So that's actually Li hat. So that's easy to write. So we know that at least in one of the reference, at least some of the vector quantities in one reference frame are easier to write. Okay, so minus omega 0 square. This is Li hat minus alpha 0. This is k cross Li, k cross I is j, so that's minus alpha 0 j hat minus 2 omega 0 times V relative, k cross I is j, and then plus A relative I hat. So this is the equation that is simpler to write. And actually, if you see, it makes sense to try to write this vector equation, which is usually the longer one, because you have all these relative velocity and relative acceleration terms in a reference frame where it would be easier to write them, right? Rather than have to choose this equation to be written in the moving reference frame. Okay, so now we have 3 and 4. Let's equate 3 and 4. So what do we get? 3 and 4. 3 is this. Okay, so this long expression over here, and the 4 is this. So let's do that. I really want to do this. Okay, A0 minus omega 1 squared r sine theta minus, and I'm going to write alpha 1 as A0 over r times r cosine theta, and that's I hat term. So that should be equal to the I hat term of the of the equation number 4, which is minus omega 0 square L plus A relative. Okay, let's call this equation 5. The J hat term in 3 is minus omega 1 square r cosine theta plus alpha 1 r sine theta equal to, now the J hat term in equation 4 is minus alpha 0 L, and then one more. That, let's say, is equation 6. Okay, so now let's identify the unknowns. If we have only 2 unknowns, we should be able to solve for them, right? Okay, so A0 is one unknown, omega 1 is known. Okay, A0 we already accounted for, omega 0 is known, A relative is another unknown. Okay, omega 1 is determined, alpha 1 is the angular acceleration of the disk, which is also actually we can express in terms of A0. So this is actually A0 over R. All right, so that's still one unknown. Alpha 0 is also given to you. So alpha 0 is the angular acceleration of the slotted link over here. So if, let's say, if the problem said this is constant angular velocity, then alpha 0 would be 0. That would simplify things a little bit, but even if it is not 0, it doesn't matter. This will be also known. Omega 0 is known. V relative we just determined from the velocity analysis. So the only 2 unknowns are A0 and A relative, right? 2 equations, 2 unknowns. We can solve for both of them.